Hello everyone. So we're going to walk through some problems here on the free fall kinematics practice. I am not going to do all the problems. I'm going to do 3 out of the 5, just so that in this occasion you actually get to do some work on your own, and we get to see you actually putting in practice what I'm trying to teach through these videos, okay? So first of all, you can see that I have the assignment right here, and then I have my Canvas board right here. I'm going to open my period 2 class just because it's the first one popping up there. And I am going to go into my homepage to find my formula chart. So as we have talked about this before, remember that you always have to have your formula charts open so that you can get the material that you need quicker and you do not have to waste time. But also, it'll help you figure out how to use a formula chart that is going to be used in the test. So this is a good tip for anybody taking or training for SAT, ACT, because if you don't know where the formulas are, then you really are at a disadvantage whenever you are taking the exams, mostly because those exams are timed. So to be able to do things right, you want to do it as quickly as possible. I'm going to go ahead and pick up my pen here. Let's see if I have the right size. Okay, very small, very good. Okay, so right here, let's go and see. So we're going to talk about free fall. Free fall just means that an object is falling, and the only thing that is affecting it is going to be gravity. So when we look at the formulas, these are the formulas we're talking about. We need to be looking at all of this. Also notice that right here, gravity is included and it's giving you the value of 10 because that's the value that is being used on the test and in most AP exams. The true value is 9.81, but it's harder mathematically and the numbers can be inaccurate whenever we are doing multiple steps in an equation. If people don't round, if everybody doesn't round the same, then the answer is not going to be the same. So as a general thought, we as physicists decided that 10 was going to be the number since it rounds up to it. Okay, so these are the same equations as the kinematic equations. They are just rewritten in terms of the y-axis. So if you notice right here, displacement is x, and displacement is still x in graphs. It's not going to be any different. The only thing that is different here is that we have put in the y for the y-axis because when we're having something falling, it's falling in the vertical axis, and we're having the letter G for the A to indicate that gravity is what is going to be the acceleration. But the formulas are exactly the same. It just has those substitutions in there. If you are more comfortable continuing to use this and you understand them, that's what I do personally. But since this is in your formula chart, we are going to use them here just so that you understand what it means, okay? And I don't want you to get confused whenever you see that in the test and then you assume that it's like completely different formulas, okay? All right, so right here you have a small child holds a water balloon 1.8 meters above his sleeping sister head, okay? So we got this little kid right here kind of like not being very nice, right? And it's having a balloon right here. And that balloon is going to fall on this girl that is sleeping. Oh my gosh, this is an awful picture. These are extremely long arms, but it doesn't matter. You get the point. This right here, this distance is 1.8 meters. So it's fallen 1.8 meters. And because it's fallen, you need to keep that in check because anything that we have in downwards motion, we're going to assume that this is 0 and then this is fallen. So this is going to be negative 1.8, okay, if it's fallen. When he releases the balloon, how long will it take? So they are asking for how long will it take. That is time. That is time. Okay? And that's it. That's all we get here. Now, one thing that you need to notice is that when you're holding something up and you're dropping it, you just hold it up and you're dropping it, it's also giving you one thing that it doesn't tell you, and it's giving you the initial velocity because you're holding it. So the initial velocity is 0. You need to know that because that is going to make it so that you can actually find a formula that works. If you don't have that, you won't find a formula that works, okay? And you need to understand that this is the distance that is falling, so then that's going to be either your x or your y, okay? X because it's distance, y because it's in the y-axis, it's vertical, and it's negative, so it's 1.8 meters. So now let's look at the formulas right here. We got to find time. That's what we need to find, right? That's what we're looking for. So our formula has to have time in it. So this formula gets eliminated because it's v, v, g, and y. It doesn't have the t. So it has to be one of these two. So now this one has final velocity, and I do not have final velocity given in my problem. So I'm not going to be able to use this one. So we're going to try to use this one. This one has x or y. This is the same as this one right here, okay? Equals VIT. So we have initial velocity and t is what we're looking for. And then 1/2 gt squared, where g is gravity. And we know that gravity is 10. So we want to write it here also. Let's just make sure that we don't forget that gravity is acceleration and that it is negative 10 meters per second. So it's not written here as a negative, but you need to know that you need to put the vector in your math so that it makes sense to you whenever you're actually solving the problem. Gravity is acting downward, so that's where the negative comes in. So remember that vectors are going to have not just magnitude, which is that 10, but also the direction, and that negative sign is the direction. And in physics, especially in kinematics, these signs are very, very important. So gravity is the acceleration, so I'm going to write the formula. I'm going to use the one for free fall, the one that is written in terms of free fall, just so that there is no confusion whenever you go to your formula chart. But again, it's the same as the previous one, and I have no problems if you choose to write the original one and you know that G is A and you just substitute, right? So all you do right here, once you write this formula, and all I did was copy it down, is I'm going to substitute, okay? So my y is negative 1.8. And that equals vi, which is 0, times my time, which is what I'm looking for, so I don't know it, plus 1/2 times the acceleration, which is negative 10, times t squared. Okay? So that's all that it is. All you do is now you try to solve as much as you can, and you're solving for t. You want to find out what t is, okay? So when you multiply 0 times something, you get 0. So that number doesn't affect the rest of our equation, so it goes away. So when we simplify this, we're going to say we got negative 1.8 equals 1/2 times negative 10 times t squared. Okay? So we can still simplify this further. 10 divided by 2 is the same thing as 5, or 10 multiplied by 0.5 if you wanted to change this by 0.5. Whatever makes your life simpler. So we get 1.8 equals negative 5 t squared. And now it's really simple, right? So now we have negative 5 multiplied by t squared equals negative 1.8. So now we just got to get, since this is multiplication, we got to do the opposite, right, to get rid of it. So we divide by negative 5 on both sides. And we get t squared right here because these two cancel out. And then negative 1.8 divided by negative 5 is what? Let me see. That is 0.36. Okay. So and it's positive because when you divide a negative by a negative, you get a positive answer. So this right here is going to be very important that you notice time can never be negative. So if you have a negative time, you put a vector somewhere wrong. And to get rid of the square right here, you need to get what? The opposite process of having something with an exponent is to take the square root of it with the square root. Okay, so we'll take the square root of both sides, and then this is going to be t equals 0.6 seconds, and that's your answer, right? Okay, so now I'm going to erase this so that we can do our graphs because I wrote all over it. So you may want to organize yours better than mine. The answer is 0.6. I'm going to rewrite that somewhere over here. But I really don't have to. You can always rewind this video and get back to your answer, right? I'm going to just erase it so that we can draw the pictures of the graphs. And I'm going to do the graphs this time on this particular problem, just because I noticed that in the previous one, several of you did not even bother to do the graph. And I think that that's mainly because I was doing the problems and I didn't do the graphs. It doesn't mean that you don't do the graphs. You got to do the graphs, okay? So I find it easier to start with the information that is given to me. So it's saying that it starts at 1.8 meters above the sleeping head. So it's going to be like high in the positive axis. And because it starts with a zero velocity, it's something that it starts low and then it speeds up. So that would be my graph for position versus time. So how did it change it in displacement, position versus time? Now, velocity is the slope of this graph. Okay, so if you were to actually figure out the slope of this graph in every section, you cannot say that it's the same, right? Because right here we have a different slope, almost a zero slope, right? And then right here we have a much bigger slope. So how you take slope? You take your y2 minus y1. You find 2 points in the graph and you do y2 minus y1 and divide over x2 minus x1, right? You find the coordinates of those points and you get the y over the x, the difference of the two, and then you subtract, and that's how you get your slope. So if you do it right here, you get a much steeper slope than if you do it right here, which means that this slope is going to be a higher number than this number right here. So when you're doing your graph, remember that the velocity started at zero, and when you try to do the slope right here, that's kind of like almost zero. So it's going to start at zero, and it's going in the negative direction, increasing. So if you do your graph this way, it's a straight line, you will have the same, you will have a smaller velocity right here and a larger velocity right here. And you may not see it because this is in the negative axis, but when you put numbers right here, let's say right here, okay? This is zero velocity, and now it's 5. That means you were going at 0 meters per second, and now you're going at 5 meters per second. Now, this is in the negative axis because this is going down. So the magnitude is independent of the direction. Keep that in mind because an object that is down here is a very fast object, okay? It's just going in the negative direction. In this case, it's going downwards. It can be going backwards, okay? All right, so I'm just gonna erase this now so that we can move on to a second problem. Make sure that I don't have anything on my screen. Okay, let's go on to a second problem. Let's see. This one right here is the same kind of situation, something falling off a cliff, but instead of asking you to get time, it's asking you to get how fast it is, okay? So you're going to do the same thing that we just did, but you're going to figure out the formula that is going to help you find final velocity. And something to know is that when we're talking about a falling object and we're talking about final velocity, we're not talking about when the object hits the ground and the velocity is 0. We're talking about right before it hits the ground. So that's what we call terminal velocities, right before the moment, okay? All right, so we are going to, I'm gonna do the one with the rocket because this is traveling in a different direction, okay? So here, the previous problem that we did was something falling. This object is going up. It's a rocket. It's initially traveling upwards, right? So with a velocity of 10 meters per second. So this is going to be your VI, your initial velocity. And when it burns out, means that it is 0, right? It stops. How much higher will the rocket travel before stopping? So it's actually telling you, it's actually, when it burns out, right, it's saying, what is going to be the distance that it has gone when the final velocity is 0? That's what it's asking you to do. How far up is going, okay? And also, you need to remember that gravity acts in a vertical direction. So if you're going up, gravity is pulling you down. That's why you stop moving at some point, because you stop being able to overcome the force of gravity. So when something does not stop, then they can break through the atmosphere and then get out into space. But when it does stop, like if you throw a tennis ball, right? The tennis ball has a maximum point that it reaches, because at that point it has no more push to keep on going forward, and velocity and gravity wins. So the acceleration keeps on acting downwards, right? So that's gravity is acceleration, but when it affects something that has mass, it turns into a force. So gravity is the pull on an object, and that's what we call weight, right? What gives something weight is gravity. It's the action of gravity on a mass. So Newton's second law, force equals mass times acceleration, and in this case, the force is going to be mass times the acceleration of gravity. So gravity acts here because it's acting down, and that is again negative 10 meters per second square, okay? So we're going to, this is our initial velocity. This is going to be our final velocity because we want to find out when it burns out how far it goes, right? How much higher it goes. So when we have a rocket, right here, my final velocity is 0. Right here is my initial velocity. This is the same thing with any object that you throw upwards. Right here, you put a force to it, right? You push it, you throw it. This is what it gives its initial velocity. And right here, that force is overcome by its weight, so which is the force of gravity acting on its mass. So right here, it stops moving. It's the final velocity of this segment. If you were looking at this way, this would be the initial velocity, which is also why this is 0 whenever we're talking about something falling. And right here, right before it hits ground, it would be final. So if you think of your hand, when the ball is sitting on your hand, that's not velocity, right? When you let go of it, that's when the motion starts. That's when your initial velocity is. So it's the same way right here. When you're talking about the final velocity in this situation, it's right before it hits your hand. Okay, so we're gonna look for displacement. That's what they want us to find, like what is the distance right here. And remember that because this is in the y-axis, in our equations for free fall, x is gonna be y. So let's look. We need to find y, so it has to be there. So this one has y, and this one has y. This one has no y, so we're just not gonna use that one. Now, this one right here has initial velocity and has time. Oh, but we don't have time. I'm looking over again and I don't see that we have time. So let's see this one. It has final velocity, which we know is 0. It has initial velocity, which is given to us. Acceleration and gravity. So this is the one. This is the one we have to use, okay? So here we go. V final equals VI squared plus 2 gravity Y, okay? So let's substitute it right away. We have all the variables right here. We have our picture. We have our formula. So we just can go straight into solving, okay? VF, we said is 0. There is 0, okay? So VF is 0. VI is 10. So 10, and don't forget your square that is in the equation, plus 2 times G, which is negative 10, times Y. That's what we're trying to solve. So we don't know it, right? This seems that it's going to be actually a really easy problem, even though it looked not so easy, okay? So 0 equals 10 times 10 is 100, plus 2 times 10, negative 20, Y, right? So now we subtract 100 right here so that we can have this by itself. So we got to do it on both sides, right? So we got negative 100 equals negative 20y, right? And now we got to divide by negative 20 to leave the y alone. Okay? So 20 divided by, 100 divided by 20 is 5. And that's and this cancels out. So my distance is 5 meters. That's how far up it went at this speed. Okay? All right, so I'm going to erase this so that we can do the graphs for this. Problems kind of like look difficult, but it's the figuring out what the problem is actually saying. If you know your variables, if you understand what the problem is saying, then it's a lot easier for you to do. Okay, so in this situation, the object starts at 0, it's on the ground, and then it goes up and it stops, right? So, and it's slowing, it's faster at the beginning, and then it slows down at the very top. So we have, that is the shape, which is exactly the shape as how we would draw it. It stops right here, right? So now let's see how we do the velocity graph. Right here we have a high speed and it ends up on 0. And again, this object is accelerating because we have gravity. So the velocity is not going to be the same all throughout. So it's not going to be a straight flat line. That's what the velocity being the same means, okay? If the velocity is changing, you're going to have a diagonal. So right here, we're going to start with a high number because right here the velocity was faster. Think of the rocket is faster at the beginning. So it's going to start at a high number. And actually it's going to start at 10 because that's the initial velocity. If you wanted to put it, you could. And that it's going to end up at what? At 0. So in a straight line, I cannot draw this straight, but you're going to go to 0 because right here, this velocity is 0. And if you wanted to put a number, that velocity starts at 10. Okay? So this is how you do your graphs. You got to think of what the graphs mean and what they are actually telling you. Okay? All right. Let's do one more problem and then you're on your own. And I'm going to do the very last one just because that's kind of like the same motion and is the one type that gets students confused a little bit. All right, so a tennis ball launcher shoots a ball straight upwards with an initial velocity of 30. So this is my initial velocity. What will be the velocity of the ball? So we're looking for final velocity after 4 seconds have passed. So it's giving us time. Okay, that is time. So remember that this is a tennis ball that is going to go like this. We don't know if it is going to be 0. We know that right here velocity is 0, right? But we don't know that that's where the object is going to end, because it's just giving us a time. They want to know what the velocity is after 4 seconds. So the initial velocity is 30 meters per second. So let's remember that because we're throwing this up and down, obviously gravity is acting on it. So gravity is negative 10 meters per second squared. Okay, so let's look at our formulas. We have to find final velocity. We have time and we have gravity. So we get time right here. We need to find final velocity. This one doesn't have time. And this one doesn't have final velocity, so it has to be this one. Yeah, we have everything. That's actually too easy. I don't know why I chose that one, but that's okay. Final velocity equals final initial velocity plus acceleration times time. We have final, we have initial. We don't have final. That's what we're looking for. We have the initial, we have acceleration, and we have the time. So we're going to find out what the velocity is when these other conditions have happened, okay? So final velocity is what we're looking for, so we don't know it. Initial velocity is 30 plus negative 10 times 4. Okay, so this is 30 plus negative 40. So that means that the final velocity is negative 10. So if I were to show you this in a picture, you would need to put the object right here, because this is the negative side of the velocity. That's where the object is at, and the negative side, okay? Because my velocity ends up being negative. See how important it is to have the signs? So let's talk now about, I'm going to write this over here. Final velocity is negative 10, because that's going to change. That's going to determine how I make my graphs, okay? So I'm just going to erase this so that I can do my graphs. Okay, so now, all right, the object was launched upwards and it came somewhat down, okay? So you don't have to be super accurate here for me, because I'm not asking you to calculate displacement. If I did ask you to calculate displacement, you would have to have the scale right here and actually stop where the ball stopped. But it is on the negative side, so long that you do that, I'm good. Now, in terms of velocity, you do know that this is a negative velocity, and you do know that it starts at 30. So you can start right here with a velocity of 30. We know that it's accelerating, right? It slows down, and then it starts to move forward again, like it starts to speed up again. So we have to start at the negative. We get to 0, that's right here. And then it goes a little bit further down. It doesn't go all the way down because it doesn't reach the ground, okay? To reach the ground right here, how do you know that it would reach the ground? This final velocity would be negative 30 meters per second. Wouldn't that make sense? So if nothing is affecting this, if there is no air resistance, if there is no wind or anything like that, then this object has to start and end with the same velocity, because the only thing that is affecting it is gravity, and that is constant. Okay? Well, that's that. So we're going to stop this recording, and you are in charge of completing the rest of these problems. Ask me questions if you need to.